Welcome to the third video on applications of forces for the stats and mechanics section of the Year 2 A-level maths course. So last lesson we were looking at equilibrium points with smooth surfaces. Now we're going to have a look at equilibrium including objects with friction. So what we're going to do here is get warmed up with a couple of fairly difficult warm-up questions to get you in the mood. So here they are. I'd like you to try these questions individually on your own without any help, and then press play when you're ready to see how they might be done. As ever, draw out the diagram fully and then resolve accordingly and add on any missing information. So press play when you're ready to see how these are done. So let's have a look now at question number 1, warm-up 1. We've got this particle of mass 5 kilograms sitting on a smooth slope that's inclined at 10 degrees to the horizontal. A force of 20 newtons acts on the particle at an angle of 20 degrees to the plane as shown. Find the acceleration of the particle. Never be scared, by the way, in an exam to copy out the diagram and make it bigger and clearer. Never be thinking you need to be constrained or have to squeeze in your working. So I'm going to do the same here. I'm going to just make the diagram bigger and, in my opinion, clearer. It's a 5 kilogram mass, so I'm going to label this on straight away. So 5g. Going vertically downwards. This angle's 10 degrees. So we need to remember when we're resolving downwards, down the slope and perpendicular, like so, that if this angle's 10, then the angle I've just drawn in between the red dotted lines and the weight will also be 10. Based off that, we can now resolve. So the component of the weight acting perpendicular to the slope, this one here, is going to be 10. Sorry, it's going to be 5g cos 10, I mean to say. Whereas acting downwards, parallel to the slope, is going to be 5g sin 10. There's also the 20 Newton force which we need to add in, so we can do this now. So it's going sort of slightly downwards into the slope, so that's 20. And this angle here is going to be 20 degrees as well. So in a similar way, we can resolve this force into two components going perpendicular to the slope down and parallel to the slope, in this case, going up. So if we do this now, we'll have these two components acting in these two directions. So the component opposite to this angle will be 20 sin 20. And the component going parallel to the slope up it is going to be 20 cosine 20. And as well as that, there's also going to be a normal reaction, which we need to add in, just so it's fully labelled for diagram. So n is going to go straight up and away from the plane, like so, and that's n. So find the acceleration of the particle. So the best way to think of this is which direction is the acceleration of the particle going to be going? Well, it's going to be going up the slope. So let's consider forces going parallel to the slope. So going up the slope, we've got 20 cos 20, which will take us our positive direction going up. So let's say up is positive. So that's going up the slope. But then going in the opposite direction, going down, we have 5g sin 10. So 20 cos 20 minus 5g sin 10 5 times 9.8, which is g, times sin 10. That gives us about 10.285. So that's the resultant force going up and parallel to the slope. We can now apply F equals ma in this direction. So the resultant force going up the slope we've just calculated here. The mass of the object is 5 kilograms, so then we can work out the acceleration by rearranging. So 10.285 and so on equals a mass 5 multiplied by the acceleration. Therefore the acceleration is going to be 10.285, the answer we just had from before, divided by 5, so we can use a calculator to leave in that value, divide it by 5, and we get 2.06 meters per second squared, correct to 3 significant figures. We can now have a look at question 2 on this warm-up. So the first one, 2.06 meters per second squared. On question 2 of this warm-up, we've got very little help at all, so nothing's been labelled. We have to do all the diagrammatic stuff ourselves. So we're told it's a particle of mass 0.5. It's being pulled up a rough slope that is angled at 30 degrees to the horizontal. So let's draw that first of all. So it's a slope. Nice big diagram. Got a particle on there. It's got a weight of 0.5 g because its mass is 0.5 kilograms. So we've got 0.5 g acting downwards, which is its weight. And the slope is 30 degrees to the horizontal. So we can add this on as well. So 30 degrees here. What else are we told? So just read it carefully and add in the information meticulously. So it's being pulled up a rough slope by a force which is 5 newtons of magnitude. Now this force itself acts at an angle 30 degrees above the slope. So it's not acting parallel to the slope, it's acting above the slope. So if I just sketch on a dotted line which is going parallel to the slope, we can now imagine the force acting at this angle, angled at 30 degrees above it. So this is going to be 30. Like so. We're told it's 30 because of this information here. So just adding this in. Like so. So the coefficient of friction is 0.1. Calculate the acceleration of the particle. Well, we're told it's being pulled up the rough slope. So what will happen here is the friction will be resisting this motion. The motion will be going this way. So the motion and acceleration will be going this direction. So I'm just going to label this as either A or V, call that acceleration. And the force of friction will be opposing this motion, so it'll be acting this way, which will be mu n. Now the coefficient of friction is 0.1. You need to remember that F max is mu n, so in our case it's going to be 0.1 n, because we've been told that the coefficient of friction is 0.1. So we can now add this in, so it's going to be 0.1 n going down the slope. And the normal reaction will be going perpendicular to the slope. So already this is quite a nightmare, but we just need to carry on. So what we need to do here is to resolve perpendicular to and parallel to the slope. So we need to do this with a weight and also to this rough force, which is a 5 Newton magnitude. So if I just do the weight first and resolve this correctly and carefully, going perpendicular to the slope like so, and parallel, then the same with this 5 Newton force, going parallel to, and perpendicular, you just need to remember the basic ideas. So if that's 30, this will be 30. The component opposite to that angle will be the hypotenuse, 0.5g, sine of that angle. Component going perpendicular, like so, will be 0.5g cosine of the angle, 0.5g cos 30. Similar idea for this 5 Newton force. The component opposite this 30 angle will be 5 sine 30. And the component going along parallel to the slope will be 5 cosine 30. Now, coefficient of friction, and friction comes into play. The coefficient of friction tells us that Fmax is 0.1 n, but we don't know n yet, so n is the first thing which I suggest we try to calculate. So let's consider the forces acting in the direction perpendicular to the plane. So because there's a idea of equilibrium in this direction, the particle's not going to be moving up and away from the plane or falling in. There's going to be a balance of forces perpendicular to the plane. So the sum of the forces in this direction will be 0. So forces acting perpendicular to the plane downwards will be equal and opposite to the forces acting perpendicularly upwards to the plane. So acting up and away, 90 degrees from this slope, is n. There's also this component of the 5 Newton pulling force, 5 sine 30. That's also acting in the same direction as n. And the only force acting exact opposite to these is this component of the weight, which is 0.5g cos 30. So therefore n is 0.5g cos 30 minus 5 sine 30. So let's see what this gives us as like a intermediate step, because we won't be done yet. So 0.5 times g, which is 9.8, multiplied by cosine 30, minus 5 times sine 30. That gives us approximately 1.473 newtons. From that, we can now work out Fmax. So Fmax will be mu, which is 0.1 multiplied by the normal reaction. So 0.1 times 1.743, and so on and so on. So that'll just be 0.1743, etc. newtons. So we're getting there very slowly. Next we need to find the acceleration of the particle. So let's now consider forces acting parallel to the slope. And we need to pick a direction of motion. So let's have going up the slope as our positive direction. So the total of the forces going up the slope we've got this 5 cos 30 component here of the pulling force. And that's the only force going parallel to the slope in the upwards direction. Going opposite to that, we've got this Fmax, 0.1n, which we worked out. We need to subtract that. We also need to subtract this component of the weight, 0.5g sine 30. Now what we can do here is use the previous answer we got for Fmax, which was 0.1473. So on the calculator, I've got this still stored in, Just be careful, this was the normal reaction force. So F max was 0.1 multiplied by that, which is this. So we can use this calculator to make sure we can put in the exact answer without miswriting it or misremembering it, to make sure we don't have any rounding error creeping in. So let's now do this calculation, and I can press the ANS button to get this value here. So going up the slope, we have 5 cosine 30 minus our stored answer minus 0.5 multiplied by g, 9.8, multiplied by sine 30. And that gives us 1.7057, and so on and so on. So going up, we've got 1.7057 newtons. Just double check. Yeah, that's correct. So now what we can do is apply F equals ma up the slope. So now F equals ma in this direction. We worked out the resultant force going up the slope is 1.7057. So the resultant force going up the slope, 1.7057, and so on. That'll equal the mass of the particle, which we were told is 0.5, multiplied by the acceleration. So therefore, the initial acceleration, a, is going to be 1.7057 divided by 0.5, essentially multiplied by 2. So if I divide this by 0.5 now, I'm going to get 3.41 meters per second squared. And so that's the final answer for number 2. Probably quite a hard problem to get warmed up with, but it can't hurt to stretch ourselves sometimes. Unless it's physical stretching, that could be quite painful. Anyway, awful jokes aside, let's now have a look at the main types of problems which I want to focus on with you today in this section of the chapter. So let's just get reintroduced to some of the key ideas in solving force and force diagram questions. So friction and static particles is the particular type we're looking at today, but these suggestions apply beyond just friction and static particles. So when a body is in static equilibrium under the action of a number of forces, including friction, you need to consider whether the body is moving or not. In many cases, the force of friction will be less than mu r, so less than the maximum friction, as a smaller force is sufficient to prevent motion and to maintain static equilibrium. So in these situations, the equilibrium is not limiting. That means the equilibrium is solid. It's not on the verge of slipping, going up or down a slope. So the equilibrium is absolutely solid. However, if the maximum value of the frictional force is reached, F max equals mu r, that's when the body you're considering is on the point of moving. So the body is then said to be in limiting equilibrium. In general, the force of friction F is such that F is less than mu r, sometimes labelled mu n, and the direction of frictional force is opposite to the direction in which the body would move if the frictional force were absent. So using those ideas, let's have a look at some further worked examples. So here we've got a mass of 8 kilograms resting on a rough horizontal plane. The mass may be modelled as a particle, and the coefficient of friction between the mass and the plane is 0.5. So find the magnitude of the maximum force P newtons which acts on this mass without causing it to move, if A, the force was horizontal, or B, if the force was 60 degrees above the horizontal. So let's consider this now in 2 separate cases. So let's consider case A, then case B. So for A, we've got a horizontal force P on the horizontal plane. So just sketch this out. So we'll do the particle, just a circular-ish blob, that should do us. and label on the forces. So obviously it's going to have a weight. Mass 8 kilograms means a weight of 8g, which should be going down, and a normal reaction going up, like so. So I'm just going to label what these are. So 8g going down, normal reaction R acting up. If P is horizontal, I'll add in P going this way. And if P is a maximum force, then the friction will be limiting. The friction will be at the maximum value, so friction will be mu R. However, in this question, we're told what the value of mu is for coefficient of friction. We're told that it's 0.5. So it's still at rest, it's not moving, so we can resolve and just think about the sum of the forces in any direction will still be 0. So let's consider horizontal forces. They'll be 0. So P will be equal and opposite to mu R opposing it. Now, if this is 8g, R for normal reaction will also be 8g because it must balance the weight. There's no vertical acceleration or motion either. So P will be mu R. Mu is 0.5. The normal reaction would be 8g. So if we just sub these in and calculate, so R is 8g as well. So 0.5 times 8g, that'll just give us 4g, which we can fairly easily calculate. So 4 times 9.8, that gives us 39.2 newtons. So we can now think about B, which is going to be slightly harder. For B, the force is acting at an angle above the horizontal. So again, different system, so we need a different diagram. So if I just sketch in the particle again here, the weight's unchanged, so the weight will still be 8g, I mean to say, going downwards. There'll still be a normal reaction force acting up. And again, we're still thinking about P being a maximum, so again the friction will be limiting, it will be mu R. But I'm going to just call mu 0.5 now, because we've firmly established we know what it is. And then this force acting at an angle of 60 degrees, like so, will have a component which is both vertical and horizontal. Like so. So P going up, if it's acting at 60 degrees to the horizontal, this angle here must be 60 degrees. Apologies if some people are annoyed by these arrows not being quite vertical and quite horizontal. I'll fix that for you, and for me in truth. So the vertical component of P will be P sine 60. The horizontal component will be P cosine 60. So it's still just about in equilibrium. So in the same way, we can consider forces going horizontal. They'll be equal to 0. They'll be equal and opposite. So based off this, P cosine 60 must be equal and opposite to 0.5 R. That's equal 0.5 R. Now consider for forces in the vertical direction. They'll be equal to 0 as well, because again the system is still just about in a limiting equilibrium. So acting upwards, we have R. We also have P sine 60 going upwards. So that'll be counteracting the weight, which is acting downwards. The weight is 8g. So therefore what we can do, we've got two expressions now involving R and P. Essentially this is a simultaneous equation, so we could just substitute one into the other. And so what I'm going to suggest we might want to do here is, what we could do is just work out what R is in terms of P and sub into this one here. So from here we can see that therefore R in terms of P will be 8G minus P sine 60. So the choice I'm making here, and there's often more than one choice, this question's no exception, I'm going to substitute this expression for R into here. So now we'll have that P cos 60 equals 0.5 R, which we've just established is 8G minus P sine 60. Now we have an equation in only one unknown, so we can solve this, no problem. So what I'm going to suggest to do first of all is to double both sides to get rid of this 0.5. Double the left, we get 2P cosine 60. On this side we'll just have 8G minus P sine 60. Then if we add P sine 60 to both sides and factorise out the P, on the left what we'll have is P brackets 2 cosine 60. Then after adding P sine 60 to both sides and factorising out that P, we can put the sine 60 in brackets as well, and that will equal 8G. And finally, if we just divide both sides by this horrible expression with brackets, we'll see that P must equal 8G, all divided by 2 cosine 60 plus sine 60. So plug that into the calculator. Whatever drops out will be what we need. So we're going to have 8G, so 8 multiplied by 9.8, all divided by 2 cosine 60 plus the sine of 60. So we've got here 42.0 newtons. So as you can see, when we've got forces acting at an angle or something on a plane which isn't horizontal, it's much harder than if forces are just acting left, right, up and down. So resolving does make it trickier, but sometimes, like in question part B, there's no getting away from it. Let's have a look at another worked example now. Worked example 2. So this time I have a box, mass 10 kilograms, resting in limit in equilibrium. So first of all, let's make a note. So limit in equilibrium, that means we're going to be using F max. So friction's going to be at the maximum. So F max, which will be mu r. That's what it means here. So it's a box on a rough plane and the plane's angled at 20 degrees above the horizontal. So again, we need to start sketching out because nothing's been sketched for us. So that's 20 degrees. We'll model the box as a particle. We're told it has a mass 10 kilograms, so its weight will be 10G acting downwards, like so. Just colour code where I've got this information from as well. That's 20. Almost, it'll come as second nature eventually. Just think, resolve perpendicular and parallel to the plane, the weight. If that's 20, this angle here will be 20. The component opposite to this 20 degree angle will be 10G sine 20. The component perpendicular to the slope will be 10G cosine 20. We're talking about F max, which involves mu r, so we need to label on the normal reaction force. Oops, I'll do that in a different type of line. So the normal reaction R will be acting up and away like so, at right angles to the plane. And here, it's not saying that there's any force for part A. There's no force being applied to it, so I'll just section this off, and this can be part A only, because part B, the system's going to change. So, the coefficient of friction between the box and the plane. Well, in the absence of any external forces, what would tend to happen? This box would want to slide down the slope, obviously. If it was completely smooth or icy, that box would be sliding down. The friction will be opposing any possible motion. So for part A, the friction will be acting up the slope, opposing it sliding down. And because it's limited in equilibrium, this force here will be mu r. So we're done with the labelling really for part A. All we need to do about here is to think about finding the coefficient of friction between the box and the plane. So if we just think about forces going parallel to the slope, it's in a limiting equilibrium, so these forces in this direction will be equal to 0. So, and as well as that, the force is going perpendicular to the plane will also sum to 0. So thinking perpendicular to the plane first, the only force perpendicularly up and away from the plane is the normal reaction. So R will be equal and opposite to the perpendicular component of the weight, which is 10g cos 20. So R must equal 10g cos 20. So now thinking about parallel to the slope, going up the slope is just mu r. And now we know what r is, we can say that's equal to mu times 10g cos 20. That must be equal and opposite to the component of a weight going parallel and down to the slope, which is just 10g sine 20. So now, mu times 10g times cos 20 equals 10g sine 20. So therefore mu will be 10g sine 20, all divided by 10g cos 20. So sometimes you'll see the benefit of leaving everything in an exact form. So rather than writing g as 9.8, you can see here the nice cancellation. So 10g on top, 10g on the bottom will cancel. So mu is just sine 20 over cos 20, which is actually just tan 20. Don't feel like you need to spot that. It's just nice if you can start to see these links. So if in doubt, type it in on your calculator exactly like this. In fact, I will do just to show you. Or you could spot and notice that it's going to be the same as tan 20. So 10 times g, 9.8, times sine 20. On the bottom, 10 times 9.8 times cosine 20. That gives us 0.364 to 3 significant figures. If you just check tan 20, it is indeed the same. So that's 0.364. Part B, slightly different scenario. So for part B, let's find the maximum possible value of P after P is added on, where P is a horizontal force, magnitude P newtons being applied. But it's still in equilibrium. So again, we're going to just take this sketch and add P onto it. So a lot of information we can use from before, it will remain unchanged. So what I'm going to do here actually, a bit naughtily you might be thinking, I can just borrow some of this and simply move it along with me. So, hopefully this will work. No, that did not work. Never mind, I'll leave that blooper in, just so you can see a pretty embarrassing fail. Anyway, never mind. Let's do it the long way. So acting down, the weight's unchanged. That's still 10g. The angle's still going to be 20. The components of the weight perpendicular and parallel to the slope will still be the same. That's what I was trying to copy in and failed miserably. So that's still going to be 10g cos 20. Still 10g sine 20. The normal reaction will still be acting away in the same direction, but it may actually change in terms of size. So we can't assume here that it's going to be the same value for R. I'm running out of space, so I'll give myself a bit more space here. So now we need to add on this P Newton force, which is horizontal. So P's coming in at this angle here, straight on. That's P. And what we can do for P is resolve perpendicular and parallel to the slope. Like so. So it's acting like so, and we can use some GCSE Z angles here to help us. So if this angle of the slope is 20, then this angle here will also be 20 as well. Z angles. Alternate angles are equal. So using this, this component of P, which is acting perpendicular to the slope, this blue one here acting down and into the slope, will be P sine 20. And this component acting up the slope parallel to it will be P cosine 20. So now what we can do is think about resolving in one direction. So it's saying here that it's still in equilibrium. So let's consider this time the forces going parallel to the slope. It's still in equilibrium, so forces parallel to the slope will be balanced and equal to 0 if you were to add them all together. The way I think about it is forces in one direction will equal forces acting in the opposite direction. So going up the slope, we're going to have P cosine 20. This time, however, because it's going to go up the slope, we need to be thinking about which way the friction would be acting. So in this particular circumstance, because we've got this force P cos 20 pushing up the slope, the maximum friction will be acting down the slope. So again, this diagram is going to get a bit busy, but sometimes this will happen. So if I take P cos 20 and put it here, acting up, then F max will be acting down the slope. And that'll have magnitude mu r. So we know what mu is, it's 0.364. Can have this in later. So we'll be doing forces parallel to the slope. Let's see though, first of all, come to think of it, if we can work out what R is. So in this case, for part B, still in equilibrium, so the total of the forces acting parallel to the slope, sorry, perpendicular, will also be equal to 0. So R's going up and away, so R, that's any force acting perpendicularly up away from the slope. That must equal the forces in the opposite direction. So the components of the direction going opposite to R are P sine 20. And as well, this component of the weight, which is 10g cos 20. So we can add this in as well. So R is this. Getting back to what I was saying earlier, forces going parallel to the slope. So acting up the slope, we've got P cosine 20. That's going to be equal and opposite to mu r, because mu r is acting down the slope, plus 10g sine 20, which is also going down the slope. So this is a fairly ugly expression, but we actually have everything we need now just to plug in. So just plug in what r is. So we were told that r is p sine 20 plus 10g cos 20 from what we worked out previously. So we're going to have something which is going to look pretty heinous, but it will drop out right. So we've got p cos 20. That's going to equal mu, which is 0.364-ish. So it's still stored on the calculator. We'll use that to our advantage, so we don't have to round anything. 0.364 multiplied by r, which is p sine 20 plus 10g cos 20. Plus 10g sine 20. So if we take the time to expand out and rearrange, so p cos 20 will equal 0.364 p sine 20 plus 0.364 times 10g cos 20 plus 10g sine 20. So now if we get all the p's onto the same side, so on this side if we subtract 0.364 p sine 20, we'll have p, and factorise it out, cos 20 minus 0.364 sine 20. That will equal 0.364 times 10g cos 20 plus 10g sine 20. Now we're nearly there, so finally, if we divide both sides by this beast here, so therefore p will be 0.364 times 10g cos 20 plus 10g sine 20 all over cos 20 minus 0.364 sine 20. Now this value here is stored in the calculator, so we can make this look a bit less horrible when we type it in. So 0.364, that is mu. So let's just leave that here as our stored answer, ANS. So mu, the answer, times 10 times g times cosine 20 and plus 10 times g times sine 20 all divided by cosine 20 minus mu, which is still the answer we got stored, times sine 20. Press equals, and what we have dropping out after all that horrible stuff is 82.2. So the maximum value of P is 82.2 newtons. And it's acting at an angle going up the slope. Finally, worked example 3. This was from a past paper a long time ago, in 2003 in fact. So here we have a box of mass 1.5 kilograms which is placed on a plane inclined at 30 degrees to the horizontal. The coefficient of friction between the box and plane is 1/3, and it's kept in equilibrium by a light string which lies in a vertical plane containing a line of greatest slope of the plane. The string makes an angle of 20 degrees with the plane. So you can probably guess by now that we need to be resolving both perpendicular and parallel to this plane. So on that note, what I'm going to suggest we do is think about a force going perpendicular to the plane and the component parallel to the plane, for this tension. So the tension acting away perpendicular will be T sine of this 20-degree angle, and going along will be T cosine 20. So we may as well add on the weight as well. So at 1.5 g, that means you can have a weight of, mass of 1.5 means a weight of 1.5 g. And we can now resolve this both perpendicular to and parallel to the slope, like so. So if this is 30 degrees, we need to know almost as second nature now that this is also 30. The component opposite to this 30-degree angle will be 1.5 g sine 30, and this one here will be 1.5 g cosine 30. Let's carry on reading a bit. Okay, so the box is in limiting equilibrium and is about to move up the plane. So if it's in limiting equilibrium, that means the friction will be at the maximum, and it's about to move up the plane. That means that the friction will be acting to resist where the motion is about to happen. So the friction will be acting down the slope here. This friction will be the maximum friction, which will be mu r. So F max equals mu r, but we're told what mu is. We're told the coefficient of friction is a third. So mu r is 1/3. So maximum friction is going to be 1/3 r going down the slope. Last but not least, let's add in this normal reaction r, like so. So here we need to find the value of T. So let's think about forces going perpendicular to the plane. And forces going up and down will sum to 0 because it's in a perpendicular equilibrium. So based off that, we can say that the forces going up, which are R plus this component of the tension, T sine 20, they must be equal and opposite to the forces or components acting perpendicularly down to the slope, in this case just for 1.5 g cosine 30. Rearranging, we can therefore see that R is 1.5 g cosine 30 minus T sine 20. Now let's consider forces acting parallel to the slope, going up and down. Because it's in equilibrium, albeit a limiting equilibrium, these will sum to 0 too. So considering this, the forces going up the slope, we've just got T cosine 20. So that must be equal and opposite to the forces or components of forces acting down the slope. So acting down the slope, we've got F max, which is mu r, which is 1/3 r, plus as well the component of the weight going down the slope, which is 1.5 g sine 30. However, we worked out an expression for r previously. So if we sub this in for r, and in fact what we can do as well is multiply both sides of this by 3 to get rid of any fractions here. So if we multiply both sides of this equation by 3, this is optional, you don't have to. Then what we'd get would be T cos 20 multiplied by 3. So it'd be 3T cos 20. 1/3 r multiplied by 3 would just give us r. I'm going to put r as this form here. 1.5 g cos 30 minus T sine 20. I wanted 1/3 of this, but because I'm multiplying both sides by 3, I just end up with this expression for r. And then, of course, at the end, we were adding 1.5g sine 30. However, we also, of course, need to multiply that one by 3 as well. So 1.5g sine 30 multiplied by 3 gives us 4.5g sine 30. Next, we need to get the t's to the same side, then we can isolate them by factorising. So if I factorise out a t here to begin with, I get 3 cos 20. And if I add t sine 20 to both sides, and then factorise out that t, in these brackets I'll also have sine 20 like so. On the other side I'll just be left with 1.5g cosine 30 plus 4.5g sine 30. Finally, we can just divide both sides now by 3 cos 30 plus sine 20 to get what t will equal. So therefore, final step, t is going to be 1.5g cos 30 plus 4.5g sine 30, and then all of this divided by 3 cos 20 plus sine 20. So one final go on the calculator just to get this to drop out as we want it to. So 1.5 multiplied by 9.8 multiplied by cosine 30 plus 4.5 multiplied by 9.8 multiplied by sine 30. All of that divided by 3 cosine 20, close bracket, plus sine 20, again close bracket, and that's going to give us, to 3 sig figs, 11.0 Newton. And I think what makes that question particularly challenging is there's no real scaffolding. It just says work it out. It doesn't really say what to do. So that's really when you've got lots of confidence you can do these questions. Speaking of you doing some questions, I want you to turn now to page 139, exercise 7c, and try questions 4, and then question 8, 9, 10, 11, 12, 13. So sketch out the force diagram nice and clearly, resolve fully, and each time you do a question, check it immediately using the book. If you're stuck or unsure, ask someone you sat next to or myself, and leave a comment in the comment section if you're particularly struck, and I'll see what I can do. Once again, I thank you for listening. I hope you found it useful, and hope to see you all soon. So once again, I'll bid you goodbye for now.